Okay, so this video is the start in the treatment of error. And we can't talk about error in measurements and propagation of error, meaning how does error compound if we're using measured values to compute a new value. We can't do that until we talk about significant figures. And so significant figures is sort of the first layer of abstraction in talking about error. So it's actually it's considering error without ever really mentioning the word error. And so you learn about this in Chem 107 and Chem 108. But we never really talked about the reasons behind why certain digits can be preserved under certain mathematical operations. What we're going to do in this class is add another dimension where we think about error and how it compounds. So I'll teach you a new way to think about error rather than just memorizing these series of rules that's more comprehensive. And then we'll get to thinking about this term called uncertainty. So how uncertain we are in a reported value, which is intimately related to error. So what I'm going to do really quick is just give you a quick overview, fast overview of significant figures. So what I've got tossed up here is a value that illustrates several of the key rules associated with significant figures that you might be familiar with. So in this particular number, how many significant figures do we have? Well, it requires us to exercise several of these rules. So in this case, we're actually only going to count these digits here, which would be 1, 2, 3, 4, 5 values, or 5 sig figs. Why is that the case? Well, anytime we have leading zeros, that means zeros that are after the decimal but before the first non-zero digit. These values are not significant. They're simply placeholders. They don't tell us anything about the measured value except the scale of the measured value, but they don't retain any significance in that they pertain to the measurement at all. They're simply placeholders. So any leading zeros like this, not significant. So the first digit that is significant is this, the green value here, the 5. And then any value that has, or any zeros that are in between non-zero digits here, this one that's circled by the orange marker, those are considered significant. The 8 and the 3 are certainly considered significant. And any trailing zero is significant, but conditionally. So it is significant if after decimal. So in this case, as long as that zero is following the decimal, and it is in this case, then we consider that a significant digit. If in an example, maybe we just had the value of 50830, in this case, the trailing zero is not significant, because it is before the decimal. And in that case, this digit here is ambiguous. We don't really know, is that truly a measured value or is that a rounded value? If we were to put a decimal here, now we have an in-between zero in which this becomes significant again. So in this case, this example, this would be 5 sig figs as written. But if we were to come in here and erase this, we wouldn't be able to know whether or not this was 5 or 4. The least ambiguous way to write any of these numbers, if this were the number we wanted to write and we knew that it had 5 sig figs, we would write this as 5.0830 times 10 to the 1, 2, 3, 4. That would be unambiguously 1, 2, 3, 4, 5 sig figs. If this zero were not significant, then we would write this as 5.083 times 10 to the 4. These two numbers are still the same, but the second one only retains 4 significant figures. Similarly, if we're thinking about this value, we would write this as 5.0830 times 10 to the minus 1, 2, 3. And this would be unambiguous way, the best way to write this using scientific notation.